Hello everyone. From this video, we are going to talk about the Newton's law of motion. As you know, you all hear it or learn it from high school. Yeah, once again, university we still have to introduce Newton's law of motion again. I think you already learned it, so I why not just doing very quick review of Newton's law of motion. And first of all, let me address the importance of Newton's laws of motion. Why they are important? Why every when it comes to physics, we are always talking about Newton's law of motion. Yeah, if you study in very detail, it's really damn important. It's really damn important. Okay, it tells you lots of things in physics. Okay, the conclusion is Newton's law tell you one thing. We have inertial reference frame and non-inertial reference frame. Yeah, you have inertial reference frame, and at the same time we have a non-inertial reference frame. For this class, I think I just talk very little about non-inertial frame. Yeah, we'll give you an example. And the Newton's law of motion give you equation of motion. It's more general equation of motion. In the last, when I did the 1D and 2D kinematics, I keep saying something. There's the equation called equation of motion. Xf equals xi plus vi times t times plus 1 over 2 at squared for constant acceleration motion. I call that equation of motion. Actually, that equation of motion, its origin is from Newton's second law. So Newton's second law is more general equation of motion, and we will use it a lot in the future. And the third one is Newton's third law, give you a concept called conservation of momentum. Yeah, it's also very important physics concept. Okay, the conservation of momentum can really help you to solve lots of problems. And we will talk about this later. Just want to do a quick review. Okay, so why Newton give these three laws? Because from the kinematics, we always in the previous section we have talked about the kinematics, and kinematics I say to discuss the relationship between the position, velocity, and acceleration, right? So what's the velocity? Velocity is derivative of the position vector with respect to t, and acceleration is the velocity vector doing the derivative of velocity vector with respect to t. And derivative, actually the d means change. Change, that's very important. Change. Okay. Before Newton, people ask what caused the change, what caused the motion. Okay, before Newton, what caused motion? Okay, what caused motion? Cause motion before Newton. Okay, what causes motion? What causes motion? But Newton said this is a wrong question. The correct question is what causes motion changes. That's the real question. What causes motion change? Okay, what causes motion changes? Okay, the key point is the change. Okay, not the motion itself. Not motion itself. We don't create motion. Okay, we only create. Okay, we can say force not cause motion. Force not cause motion. Force cause motion changes. Okay, force will not don't cause motion. Okay. So change is very important. That's the Newton's opinion. Change is very important. Right? So just like I said, Newton said force cause motion changes. Force. Mm-hmm. Mm-hmm. Its force cause motion change. Its force cause motion change. Force, that's very important concept. Force cause motion change. And what force we will have we will have in the daily life. And very simple. The spring force. Okay, spring force we will we will talk about the spring force a lot this semester. And tension is the daily example of forces. And the friction, yeah, friction is also the daily example of forces. And force cause changes. And when you place something, an object on the surface will give the object a called normal force. Okay, normal force is also very important because without normal force, because force cause change, if the surface doesn't have the normal force to the object will keep sinking down into the surface. Okay, so that's why normal force keep the object on the surface. Actually, when you have a mass push on the surface, you push the atom. You push the atom on the surface, and after all, this atom will have some counter force to balance the force you give them. Okay, and the spring force, tension, or normal force or friction force. These are we can call contact forces. And the next semester, when we do the we will study the electromagnetic force. And electromagnetic force is called action at a distant force. Actually, gravity is also action at a distant force. But this semester, I won't touch the gravity. Okay, I think electromagnetism is more important for engineering student. And for the electromagnetic force, because I think you all learn from high school, the Coulomb force between charges, there's nothing between the charge, but they can still feel the force. And the magnet, yeah, there's no object between these two magnets, but they can feel the force to each other. Okay, that's called action at a distant force. Okay. And the next slide, this slide just show you some example of action at distant force. And in this video, you can look at yourself. It's very interesting, but we will talk about this action at distant force in next semester. Okay, let's give you a sense. It's action at distant force. And the force is a vector quantity. So force is a vector quantity. So when you do the force analysis, yeah, you can do it component by component. Yeah, just like you did in velocity and acceleration and two-dimensional kinematics, component by component. Force is a vector as well. And the Newton, okay, let's finally reach the Newton first law. What Newton's first law said? It says a body in uniform motion remains uniform motion. So what's the uniform motion? Do you still remember that? What's the uniform motion? Uniform motion is uniform motion. What's uniform motion? There are two types of uniform motion. Yeah, you will see it every day. You stay at rest. It's you call uniform motion. You put something in front of you, stay over there. Yeah, that's called uniform motion. And the other is constant speed, constant velocity, and more important, straight line. Okay, STRAIGHT, straight line. Constant velocity and straight line is also a uniform motion. So uniform circular motion, that's the textbook talks about uniform circular motion. Is a uniform motion? No, this is not uniform motion. Uniform motion is at rest or constant velocity in straight line. Okay. Alright, so and the next and so it say unless the body will keep in uniform motion, remains in uniform motion unless it acted on by a non-net forces. Okay, so uniform motion at rest or doing constant velocity straight line, and if we change, for example, from rest it stay at rest and then keep and becomes the object starts at rest and then becomes moving. That means it's acted on by a non-zero net force, or you have you and you or you have a or you have object doing a constant velocity straight line and then it stop or it gradually stop. That means it's acted on by a non-zero net force. Okay, that's the first. That's Newton's first law of motion says. Okay, stay at rest. If the yeah, if it, in Chinese, okay, if something stay at rest and then it's keep at rest. If something keep going the straight line and with constant velocity and keep doing the same thing, straight line and constant velocity, as Newton's first law say. In fact, Newton's first law of motion it gives you the inertial reference frame, but we'll talk about later. Inertial reference frame. This is important to define inertial reference frame. Like I say, the conclusion one is inertial. The Newton's law, the conclusion of Newton's law is inertial reference frame. So what's inertial reference frame? Okay, that comes from the first law, Newton's first law of motion. Okay, so let's keep continue. Okay, let's continue. And there's some in the video example to show Newton's law of motion, so I'm not going to do it in the video. Okay, so and the next Newton's second law, and Newton's second law says that's here. Newton's second law, which one is? Okay, this one. This is Newton's second law. Newton's second law equates the rate of change of momentum to net force on object. Okay, it's difficult to read this sentence. Newton's second law equates the rate of change of momentum to the net force on an object. Okay, so typically if written in mathematics, it just says the net force. Okay, net force means the vector sum of the force. So you will see some textbook writing this way: summation F equal to dP over dt. Okay, that's a net vector sum of force. Vector sum of force. Vector sum of force equal to the rate of change of momentum. So rate change, that means doing the derivative of momentum with respect to time. That means the rate of change. Rate of change momentum means doing the derivative of momentum with respect to t. Okay, so there's a problem. So there's a problem left. What is momentum? Okay, that's the momentum. We will talk about the momentum more on Newton's third law. Okay, this is the momentum Newton defined to call a quantity of motion. Okay, in simple way, it's the mass times velocity. Mass times velocity. I think you all learned it. And mass times velocity called momentum. But this quantity of motion actually comes from the third law. Okay, but I think this comes from the third law. From the third law, you will see you will have a quantity of motion. Okay, and then Newton called momentum. It is equal to mass times velocity, and we will talk about it more on Newton's third law. Okay, let me just keep continue for this. Okay, do a quick review, and we'll talk about detail later. Okay. The next one is from Newton's and Newton's law. The importance of Newton's second law is it gives equation of motion. Okay, so why? So let's do a little. Math here. You say the summation F equal to the derivative of momentum with respect to t, and the p, like I say, we just say the p equals to mass times velocity. Okay, so and then we do the product rule. Okay, the derivative has product rule. Okay, we have two terms. Okay, and these two terms, from a simple problem, the mass doesn't change with time. So the derivative of mass with respect to t is 0. So we will this left equals dimension f equals to m dv over dt. Okay. Okay, so yes, in simple case, the mass is not a function of time, but in some very difficult problem, I just mentioned it because for the rocket, if you want to launch a rocket, then the rocket, its mass is not a function of time because rocket you have to load a lot of fuel and the fuel go to explosion and make a thrust to push the rocket to the air. And in the rocket science, in the rocket dynamics, your mass is not a function of time. So it makes the problem more difficult. But we are not talking about, we will not talk about the rocket problem in this course. So I just mentioned to you in some difficult problem, mass is not a function of time. Okay, maybe in some fluid dynamics, mass is a function of time. Okay, so for this course, the mass is not a function of time. So we will have this, and okay, to further and we all know the velocity is equal to position derivative of position vector. So finally, we'll reach this equation. It's doing so times m. Okay, this is equation of motion. Okay, and this equation of motion is equivalent to the equation of motion I show you on the 1D kinematics and 2D kinematics. They are equivalent, and this more general equation of motion. I will do a quick video to show you why this is why it's more general equation of motion. But we just mention it. Okay, because I have some other content to tell. Okay, so I will do a video to show you why this is equation of motion, and this is more general equation of motion. Okay, and the next one is what's the unit of the force. Okay, the force is mass times acceleration. Okay, so it's obviously the unit of force is just mass times acceleration. So the mass in MKS system, mass is kilogram, and acceleration is meter per second square. So the Newton is equal to kilogram times meter per second square. That's Newton. Okay, that's definition. Okay, and from the Newton's second law, and just show you F equals dimension F equal ma. Just a concept, final concept. Okay. Okay, mass. Okay, you can see the mass. Mass has another meaning. Mass is resistance of object exhibit to change in its velocity. Okay, so and next time we just that's the slide we just said. F equals to ma. So let's use F net. Let's get rid of the vector, just makes it simple. F equals to ma. So we can just make a reverse of this equation and say, let's say A equals m 1 over m f. So you see this when you can look at this equation in this way. So this is your input. Force is your input, acceleration is your output. Okay, so when you apply force to your system, okay, and if your m is large, your acceleration is down. So if m is small, a is great. So actually the mass it can be represented as the resistance to your applied force. Okay, mass can be viewed as a resistance. Okay, that's a concept you should remember. Mass can be viewed as a resistance, and this concept used in maybe later in the force oscillation or tempo oscillation. Okay, mass can be viewed as a resistance of your applied force. Okay, the same applied force. Yeah, same applied force. If your mass is up, your output is down. Yeah, because it's difficult to move, and your mass is small. Same input. Your change on acceleration will be huge. Okay, so mass is a concept or can be viewed as a concept of resistance. Okay, so that's also from Newton's second law of motion. And the next one is just a simple concept. The weight and mass are different. Weight is a force. Mass is just a mass. Okay, that sounds pretty like very trivial. Yeah, but that's just a concept. Okay, weight is a force, and mass is just a mass. Okay, so it's different. Weight equal to mass times acceleration. Ration. So in the Earth, we have acceleration g. Okay, so weight is acceleration dependent. Weight is acceleration dependent. If you're on different planets, your different planet have different acceleration of gravity. So at the different planet, you have different weight. Okay, but the mass is always the same whenever you are in different planet. Even you are in Mars and you are in Moon, your mass is always the same, but your weight it will be different on the mass. It will different on Mars and Moon. Okay, that's Mars and Moon now have different acceleration of gravity. So let's just give you because many people misuse weight and mass, really. Yeah, especially in many articles, in the misuse mass and weight. Weight is a force, mass is just a scalar. Okay, mass is intrinsic property, weight is intrinsic property. Okay, so that's the quick review on the law of the first two law of motion, and we will do a review quickly in the next video. So here, this video I just stop here and see you in the next video. Bye bye.